Hi everybody, welcome to another Isodate TWF arcade repair video. This time I'm going to service a Zaccaria Space Pirate board set. The main logic board is actually made by Cinematronics. This game is a bootleg of their Ripoff arcade. This is a vector game, by the way. This other PCB has the audio effects circuits, but also the digital to analog video converters. These are two 10 bits DAC chips. This PCB was entirely made by Zaccaria. The last PCB of the set is a credit adapter circuit. Of course, I first dumped and checked the EPROMs against the non-dumps of this game. The EPROMs are 2716 type, as it can be seen by lifting one label. This board has been already serviced in the past. Lots of ICs are already socketed. However, the bottom side of the PCB was left with many solder flux residues and suspect damaged trays. Here we can see some other reworked ICs. Flux residues are not too bad, but some joints don't look too good. Here is another reworked area. I'll take some time cleaning all residues and inspecting the pads and traces for any visible damage. After cleaning and reflowing a few joints, here's how the PCB looks like. The last thing I've noticed is a missing electrolytic capacitor here that is right at the power supply input, so I'll install a replacement later. This capacitor is not going to make any difference during the troubleshooting of this PCB anyway. I've also got the interconnecting cable for the video data and the one for the audio part, but not the connection cables for the credits PCB, so let's see what I can do. First of all, let's understand what's the function of this circuit board. Here we can see the original Cinematronics game credit options. There are only 4 possible settings. However, the Zaccaria game provided a lot of different credit options for various foreign markets and 2 independent coin mechanisms, as you can see, that can be configured separately. There are 8 total dip switches to configure the 2 coin mechanisms and quite a few label options for different countries. This large set of credit options has been realized by adding an adapter logic board that connects to 2 coin switches that are the inputs labeled NO and C on the left side of the schematic, and on the other side is connected to the original coin inputs of the main game PCB via the contacts, again named NO and NC on the right of the schematic. The various dip switches present on this circuit will decide how many consecutive pulses are delivered to the original game board to mimic any wanted credit per coins configuration. Anyway, as for every other circuit, I'll start checking all the diode and transistor junctions with the multimeter. Having found no suspect junction, I've then proceeded at checking all electrolytic capacitors with an ESR meter. The only one that had a suspiciously high ESR value is this one that happens to be the main giving capacitor for the clock source of this logic board. So I decided to remove it and check it with my LCR meter. Its capacitance value is correct, but it's different from the value reported in the schematic. Anyway, I decided to replace it with a film capacitor that has a much lower dissipation factor and is better suited for a timing circuit. Here's the substituted capacitor. This is also much more reliable than a tantalum one. Now, to simulate a coin switch with normally open and normally closed contacts, I'll use an old mouse button micro switch that almost always has both the contact options that I need in this case. So I have connected the micro switch to the coin input number 1 with the common contact going to a ground pin. And then, as you can see here, the coin PCB also needs a 5V supply. So I connected some more wires to the appropriate pins to hook the 5V needed for the PCB, and I'm now ready to see what happens. I am going to check the output pins to the motherboard with the logic probe. And now let's simulate a coin session with the switch. Nothing happens. Let's check another output. And nothing also here. So let's first see if the switch is working. Yes, it seems fine. Both contacts are toggling. So I started checking signals in the various ICs of this circuit, but to make a long story short, I've quickly realized that a good part of this logic design needs both the coin switches connected, at least to the normally closed contact to ground. Otherwise, most of the clock distribution and AC-enabled signals are shut down. So I've now grounded the NC contact of coin 2 input and I can try again. And yes, now this output pulses. And also this one does. So far so good. Now the switch is connected to coin 2 input and the NC contact of coin 1 is kept grounded. And that's good. Each single coin action produces more than one pulse since I've configured the dip switches for 3 credits per coin. I think that this board is working fine. Before the actual power on, I wanted to show a little unusual fact about this Cinematronics Vector Arcade. This logic PCB has no integrated CPU. The main processing unit is made with various TTL logic and PROM ICs. For example, these 3 ICs are 4-bit arithmetic logic units. The total IC count is still not high with respect to a typical arcade game of 1980 vintage, so I think that Cinematronics engineers knew what they were doing. I have connected the required power supply voltages to the logic board and to the audio-video PCB. I've also connected a speaker for the sound output. The 2 XY deflection voltages would be shown with the oscilloscope. And we have some deflection, that's good. Let's switch to XY mode. This sound should be normal even in attract mode. I actually don't know how this game is supposed to look like. I'd better go see on Mamie first. Okay, I have the X and Y inverted on my scope for sure. Of course, the simulation has no sounds, since it requires the sound sample files that I don't have. There is also service mode. Let's see how it looks like. I've swapped the deflection signals now. That's interesting. The sound seems not working anymore. This is the credits number, and both axes are actually inverted anyway. Let's start a game. Yeah, the sounds only make these cracky noises. But overall, the game seems working. So far, I haven't really checked anything on the audio-video board, so I decided to quickly check all diode and transistors, and then the electrolytic capacitor ESR. And indeed, one electrolytic capacitor showed a too high ESR, so I removed it. Here it is, dissipation factor is out of range on the LCR meter. Okay, now the sounds seems to be back, but the logic board does not always start. And look at this. As usual, these sockets need to be changed. So I've pulled all the 4 EEPROM sockets and replaced them with new ones. I've also installed the missing capacitor for power supply input bypass. Let's see if everything works now. I've decided to connect my little homemade vector monitor to have a better display. However, deflection seems not stable. That is strange. It seems it goes on and off when I move the video DAC ICs. So I've decided to replace also these last 2 red sockets. Notice that the 2 DAC ICs have opposite orientation in the PCB. This could be dangerous for an absent-minded serviceman. However, nothing changed. It is going to be embarrassing. This is the X deflection voltage. Notice that most of the time all items are drawn in a little area at the center, so actually I have to blame my monitors that's triggering its spot killer circuit for the too low voltage on the X deflection. In fact, activating the service mode gives a perfectly stable display. The squiggly lines are because of noise coming from the PC power supply I'm using. I've added some components to my monitor spot killer circuit to relax its intervention thresholds. I've also installed a jumper to restore its original behavior, which is perfect for the Atari Asteroids game that is its intended final destination. Now, with a stable display, I could play and test the board for a good amount of time. However, after a variable time, from like 10 minutes to up to a couple of hours, the sound will still completely disappear. All the different effects will just produce some crack noises in the speaker, so the fault must be in the final amplifier circuit that is common to all the different sounds. Luckily, we can test the audio board alone. When powered on, it outputs a continuous beeping sound. But after some time, the sound goes away. I'm now looking at the volume trimmer input, and we can still see the beeping signal. And the attenuated signal from the trimmer can be seen at the final amplifier input pin. So, if there is an input signal and no output signal, it must be the final amplifier IC, and I have ordered a new integrated circuit to substitute the old one. New IC in place now, and let's see if it fixes the issue now. 2 hours later, I'm afraid I'm really wrong again. Well, I was too quick in concluding that the TD-1010 amplifier was faulty. The first mistake I made was looking at the signals with the oscilloscope input set to AC coupling. Since both the input and the output pins of the final amplifier are coupled through capacitors, I should check the signals with DC coupling to discover if one of the capacitors is failing. Of course, however, I've checked the power supply on pin 3 and that remained stable, and the biasing voltage on pin 5 also remained constant, so those can be ruled out. This is the output signal when the amplifier is almost failing. We can see that the min level jumps to 0 with the scope input in DC coupling, so this is a capacitor failing to block DC. Now, on the output, we have 3 coupling capacitors, the big electrolytic going to the speaker, a small ceramic capacitor coupling a resistor filter to ground, and another small electrolytic C33 coupling a feedback pin. But notice that this last one is connecting to a more positive voltage on pin 4, so if failing it will cause the output signal to jump higher in level and not to ground, as we have just observed. Also, if it was the speaker coupling capacitor, it would be enough to momentarily disconnect the speaker to eliminate the signal jumps, but I've tried that and it does not stop the fault. So this only leaves the small ceramic capacitor, and I'm going to substitute it with a film capacitor that will be much more reliable anyway. So here is the new film capacitor. And let's try again from this time. Oh no, I'm wrong again. The output just started to jump. Since I was already wrong a few times, I decided that one more time would not make much difference today. So I'm going to substitute C33 even if it cannot be causing the output DC bias to go to 0. And by the way, at this point I still don't understand what the real issue is. Here's the new capacitor and the new start time. And obviously it failed again. Another mistake that I obviously made is to only look at the output pin, assuming that the failing DC level couldn't be instead caused by a failing DC bias at the input of the power amplifier. Here we can see that even the input of the amplifier has a DC coupling capacitor, circled in red in this schematic. So far I only checked the input signal with the scope input set to AC coupling. However, looking at the tantalum capacitor, I realized it's connected in the wrong way, so let me remove it. This is the trimmer side. The signal has 0 volt DC level, and the scope coupling is DC. And this is the amplifier input side. And here we see about 1.5 volts positive bias. The signal going to the P1 volume trimmer is coming from a TL081 operational amplifier with the non-inverting input grounded, so its output will have a 0 volt DC bias. It means the signal will be symmetrical around ground. However, the TD810 amplifier only has a positive supply, so likely its input pin has a positive DC bias as we have seen with the scope. So the coupling capacitor sees a reverse DC voltage for all its life, albeit a small one. I guess they had a high failure rate in this audio PCB back in the old days, because of this wrong design. And by the way, the old tantalum capacitor fails after some time even with the correct polarity applied. This meter of oscillating means the DC bias is shorting out. If I reduce the DC bias, the capacitor starts working again. And if I increase the bias, it keeps on working for some more time. But eventually it fails again. So now I've installed a new tantalum capacitor with the correct polarity. And finally, it just works all the time. So, this arcade game gave me some interesting problems, and I hope it was interesting for you too. If you have any question, please use the comment section below. It's all for now. Have a nice time and thank you for watching.